1 day without internet. 1 day without internet. You know how many tasks already stacked into my email inbox, and it took me so long to get everything done and give students response. All right, so let's start working on important stuff. Super important. Okay, it's something you have to know. There's no shortcut on it. Okay. What's this called? Phasor. Oh, sorry. Phasor, right? What's the amplitude? Let's say A. Same thing, right?
Are you recording?
Yes. Why?
It doesn't look like it.
Looks different?
Yeah, usually you have like a green box.
Oh, yeah. That's why it's a new software. I just reinstalled it. It's recording, yeah.
Oh.
I think it's recording. See? Since it's just a stop button, no start button. I just cannot double click and maximize it. But I think it's okay, it's fine. Alright? Same thing, same stuff. One thing you have to know, if I have A plus BJ, C plus DJ, okay? This is the same as what? A squared plus B squared. Angle, what? Arc. Tan, what? B over A. Over C squared plus D squared. Angle, arc tangent, D over C. Is anybody still have questions on this? We have spent 2 lectures time, even though it's already considered luxury for this class, for this pace. But we should spend like a week or 2 weeks to do this. But now we are reaching here anyway, so you are forced to know this. You just have to know it. Any question on this? Feel free to ask. I'm not expecting anybody is totally mastering this right now because it's been only 2 lectures. 2 to 3 lectures probably. This is the 3rd lecture, almost the 3 lectures. Is it clear? This is a polar. So phasor, right? Phasor is a polar form. This is a rectangle form. A lot of questions, right? Okay? Let me show you. This is this by definition. We just use the angle to represent the phase over here. And we use a reference because sine wave, cosine waves, they look the same depending on where you start looking at it. You set as reference at a different place, you get a sine wave or cosine wave depending on the starting point, right? Same shape. So we can just use, because this one doesn't carry time, it's just the amplitude and phase. So the problem is you can use any kind of sine wave as a reference. So we are trying to use, so for this class, we use A cosine omega t plus theta as a reference. So if I write this or this, you should know that the corresponding time domain sine wave looks like this. Another super important concept will be introduced now, okay? See. Here, they are all the same stuff. If you still have questions on this, make sure ask me during office hours, email me, do whatever you can do. And I'm gonna go through the calculation problems. I'll just let you know. This type of problem in homework 9 is the last problem on the exam. Not exactly this one, but very similar. You just have to know how to do it. I'm gonna show the calculation really quickly. You just have to understand here in order to do this. Otherwise, it's just like what I'm doing, you're totally getting lost. This to this is the same by definition, and here to here is also by definition. We just have to set a reference. Adding a theta over here, if theta is positive, assuming is larger than 0, Is this larger than 0? Yes. Leading or lagging? Yes, new word, new term. Leading, lagging. So this is leading. Just seal this in your mind, even though we probably don't have a. What's going on? That's funny. New computer system has a power setting there that I don't like. Should do power, I think. Where's the power setting? Edit power plan. Never turn it off. 4 minutes? Never. Never. For everything. Okay, we're good. So, I know it could take time to absorb this, but could you just seal this in your mind? You get a positive angle on the it's not a complex plane, whatever. This is a unit circle plane. A positive angle, that's leading. So the opposite side will be lagging. Why is that? Let me show you really quick. Okay, it's the sine wave. So if I start a sine wave from here, what's going to happen? I start here and then start rotating. What's happening? You're getting a like this, right? Because the sine theta, whenever the bar, the phasor is over here, the bar's amplitude is sine theta, right? So what is sine theta at the very beginning? 0. See, the bar doesn't have any sine value because here is sine, here's cosine. There's no sine value. Whenever it starts rotating counterclockwise, it starts getting an amplitude here. So the sine wave starts from 0, and whenever it rotates, it's getting an oscillation like this. Because it's just oscillating over here on the y-axis, but if you stretch it in the time domain, you got a sine wave. Make sense? Talk about this for several times. That's how that works. If you have an initial angle here, okay, initial angle, it takes shorter time to finish the whole circle. Does that make sense? You added angle to it, so it takes less than 2 pi to finish it. Where should you shift this thing? Left or right? Left, since you're getting a shorter period. Make sense? It's the best way to teach it this way. I mean, make sense? Leading or lagging? Leading. So positive, this is larger than 0, it's leading. Okay? In time domain, how do you figure that out? There are 2 problems on this kind of concept. They'll confuse you a lot if you don't come to lectures. So for cosine, if I draw this, right? If I just draw you a phasor, is there a phase shift? Yes, this is theta here, right? It's adding an angle. If it's positive, it's directly adding an angle here. So if you want to reflect this phase shift in the cosine theta reference, you're adding this theta over here, okay? If you're adding it to here, because you're adding a positive angle here, you're adding a positive angle here as well. So if you're adding something over here, it's shifting this cosine wave, original cosine wave, to the left or to the right? To the left. If you shift it to the left, you are making that sine wave or cosine wave shorter or longer? Shorter, because it's already adding an angle there already. So it's making that time to finish that circle earlier. So that's why it's shifting to the left, it's making it shorter, and that's the leading. This is the leading. Can you understand the whole process for this kind of analysis for this case? And there's another, it's a counterpart, it's another case which is lagging. But it's just super similar. If I tell you, like, I want to, let me finish this first. Cosine omega t, what? Theta. Plus. So plus is what? Left or right? Left. Leading or lagging? Leading. Okay? If I tell you I want to shift the cosine wave to the right by theta. Do you want to add theta or minus theta? Shift to the right. Minus. Leading or lagging? Lagging. The angle will shift to the bottom of the x-axis. Right? Make sense? This will solve a lot of problems, Draw this. I'm using sine wave as a reference, but you do cosine wave on this axis, it's going to be the same case. I'm just doing sine wave. So if I draw it this way, okay, draw it this way for the sine wave, and you know this is leading or lagging? Lagging, right? So if you look at this amplitude, so it looks like this. Oh, it's lagging because it should start from here, but however, it started the 0 point certain time amount of time, right? So it's lagging or leading. Lagging. Angle, negative angle is lagging, positive angle is leading. Make sense? Okay? So this becomes what? E, J, what? Because it's labeled as theta, so it's still theta, right? Even though it's negative. Alright?
So what's the difference between, like, if theta's like, lagging situation at 30, what's the difference between like cosine of omega t plus 330 or omega t minus 30?
Yeah, minus 30 will just shift to the right.
So is it just shifting way to the left or a little
Yes,
bit to the right?
yeah. In time domain.
Gotcha.
Okay, for phasor domain, just like this or this, right? Is that clear? Okay, so let's move forward with the calculations. Impedance stuff. It'll frustrate you if you don't know how to do it. Okay, starting from this problem. So make sure after this class, go to Canvas and go through these problems. I posted the problem set. Work through every single one. Don't just eyeball it. I know a lot of you like to just eyeball it. I think I can do it. But eventually got nothing. So just calculate every single detail about it, okay? Just calculate it, work through it. Don't trust your eyes, trust your hands. So first step. So first thing, okay, it's Ohm's law, KCL, KVL, mesh, node, parallel resistor, series resistor, all these rules apply to this. Good news. So the first step, just convert into impedance. So impedance for capacitors and resistors, they just introduce a frequency component into the resistance, but it's called impedance. Eventually, you just use it as a resistor. Make sense? So the thing is, you just have to convert it into impedance first, so you can directly just use it as a resistor for all these same calculations in the future. Is that clear? That's it. Super simple. And combined with all these phasor calculations, and you can solve all the problems. It's not difficult at all. So first, what's the resistance here? You don't have to change it. It's just resistor, linear component. No change. This guy, what's the impedance of the inductor? I taught about it. It's J omega L, right? Omega is rads, readings per second. I talked about readings per second last time. So if you're not familiar with that, definitely watch the video from Monday. But however, now I'll just ask you to remember it. You can also put on the cheat sheet if you want. But definitely for the calculations, when you're working on homework 9, you should know this immediately. J omega L. So what is omega? Where do you find omega? It's in the time domain. Time domain. It already tell you Ig is a sine wave, 350 cosine 5000 t milliamps. Never argue about that. Use that as a sine wave, but it's a cosine. It doesn't matter. People will just say it's a sine wave. Sinusoidal or sine wave. Even though it's a cosine, it doesn't matter. It's a sinusoidal wave. So what's omega? It's this. 5000 because this is cosine omega t. So this is omega. It's radians per second. What is radians? Watch the Monday's recorded video on YouTube. Alright? Definitely watch it. So J, keep J over there. Omega is 5000. L is this guy. So basically this equals J 5000 times 48. times 10 to the negative third. Okay, let's calculate it. I think I have the answer here, do I? This whole thing is J240. I think I calculated previously. So this is J240, okay? J240.
Are you recording?
Yes. Yeah. Two people ask me, let me see, let me check it. So what's the impedance of this guy? This is 1 over j omega c, okay? So 1 over j omega c is times j on both sides. On top and bottom, you're getting j minus j omega c. So you can directly use this if you want to make it faster, okay? This is impedance of this guy. And how to derive it? We don't have time to derive it. It's pretty simple to do it, but let's don't do it today. Just remember, okay, 1 over j omega c is the impedance of this guy. It's converted to impedance. And directly write down this form. And let's just plug in the numbers. What are they? Minus j over 5,000 times 2.5, 10 to the negative 6. Minus 80j. Okay? Just plug in. Plug in. Let's see what is this asking. V0, so it's VL here. Can you calculate it? Depending on what you have. You have this impedance here, you have this impedance here. Just parallel circuits, find out the currents, then you can find out the voltage. Pretty simple. So how to do it? So first IG has an angle or no? Is there a phase shift? Is this just like A cosine omega t, or is A cosine omega t plus theta? Which one? Which one? First one. So no phase shift, right? It's a standard form, no phase shift. So in the phasor form, how can you do it? It's just a constant. It's going to be 350, angle 0. As a reference, it's just a reference. If you compare to another signal, there may be a phase shift. But since we have a 0 angle here, so we're using this signal as a reference, starting point. So all the shifts are compared to this one, okay? So just directly, if this amplitude, no phase shift, don't worry about the time domain. We're doing the phasor eventually. That's why it's called steady state. You will see this a lot. Don't worry about that term. Whenever you see steady state, but all the problems are steady state in our exams and in the course scope. So eventually, this will give you all the frequency for voltage and currents. You just don't worry about the frequency. Directly just plug in later on. When you're converting the phasor back to time domain, you just put it back in. You don't have to put this in any of the calculations. Yeah, but these ones, right? The impedance. Otherwise, you just don't do it. Don't use it at all. All right. So this is the original signal, and these are the two impedance. Can you find out the current divider, right? Current divider. Do you still remember the current divider equation? If you forget it, I mean, refer to the previously recorded videos. R1, R2, I1, I2. So what is I1? I divided by R1 plus R2 times R2. So the I1 here will be the summation of the two resistors. I divided by the summation of the resistor and times the other resistor. If you have two branches. I derived this for multiple times in the previous lectures. So now let's just use it. If you have 3 branches, it's going to be different. Don't worry, you have to just calculate the voltages. But now let's just use it, okay? I divided by this times this is going to be the current over here. So now we got an overall current and we got the resistance. They are in series, right? In series. So eventually you just because this is eventually minus 80J, we calculate it over here, and this guy is J240. Okay. Okay. So you got the two resistance, even though they're in parallel, but according to the current divider equations, they are adding together. Okay, adding together. So if you want to get a current here, the current here, let's label it as I1, for example. I1 equals what? IG divided by what? These two added together, right? 240 plus or minus 80J plus 80 plus what? J240. Okay, times what? Times the resistance here, we'll get a current here. Times the resistance here, which is 80 plus J240. That's it. So now I'm going to show you how to calculate this kind of complex form. Important. We haven't done this before. So there are a lot of confusion, but it makes a lot of sense when you use phasors because it's exponential. Okay? So take a look how to do it. What is IG? Plug in. 350, angle 0. Okay? And then 80 plus J240. Let's just expand it. You're getting 320 plus 160J, right? Okay, how to deal with this angle here? So what does the angle mean? 350 this equals what? 350 what? Right? It's basically just 350, right? Okay? 0 angle. 0, 1, 350. Gone. Okay? Then calculate it. 350 times 80 plus J, 350 times 240 over 320 plus 160J. It's a lot of calculations. Let's divide by 80 first. By 2. Yeah? You can use a calculator if you have a calculator. If you don't have a calculator, what we can do? And this becomes 2 square minus J square, which is 4 plus 1, which is 5. So this is 5. It's a very common method. You just have to do it for at least like 20 to 30 times from now for the rest of the semester. So this is something you have to know how to do it. Unless you know how to make it, how to simplify it in the with the calculator, but something you have to know. Okay, and then expand whatever on the top. I'm worrying that for my calculations here, hopefully it didn't make any mistakes, but you know, just teaching you the methods. If there's any calculation, the algebra calculation, you can figure that out later. And expand it. Okay, expand it. This times this, 175 times 2 minus 175 times J plus J 350 times 3, and this times this is giving you plus 175 times 3 divided by 5. Right? Is this correct? very likely there's some errors. I just calculated in my mind. 70, 105, 175, 25 left, 175J. You just assume this is correct, okay? Assume this is correct. So if this is correct, how could we get V out? So this is what? This is the current, I1, right? This is the current here. Okay? So V out equals R times I1, which is 240 ohms times 175 plus 175J. Very likely the calculation is wrong, but you know eventually you can simplify it to a rectangular form, and eventually you times the resistor, get a voltage. Okay, so this will be this time. So eventually you're getting A plus BJ, okay? So it's asking you, so this is a rectangular form. How to convert it to the phasor form? A squared plus B squared. Okay? Angle, which is arc tangent B over A. That's the first one. You show an angle here, and amplitude and angle. Or what you can do, the E form, right? That's all the forms you can use to represent the result. Same thing. Time domain. What about time domain? Time domain. Cosine, right? Omega t. Omega doesn't change. Plus. That's it. With the A square with amplitude. Is this difficult to understand or no? I warned you guys over the weekends, right? Attending classes this week. Watch the videos. Try to understand the angular stuff and unit circles and complex plane. So see, this is a typical way to solve all these things. To here, to here, to here. Any questions? So they will ask, okay, let me ask you, what is omega? What's the angular velocity here? Omega. Does it change at all? It doesn't change, it's still 5,000 readings per second. It's not changing, it's given. What's the theta? What's the voltage? V0, right? So what is V0's angle or phase shift compared to the standard cosine wave? This. That's the angle, we calculate it. Because eventually you calculated a rectangular form of the V out, so you can convert it using our tangent form to convert it to the angle, back to the angle. So rectangular form, this is imaginary, this is real, right? Phasor, A plus BJ, A, B. This angle, what is this angle? Arc tangent B over A. That's it. That's everything about it. What's the length of the bar? The length of the bar is the amplitude, is this guy. What's the phasor? What is the phasor? I told you on Monday. Anyone can tell me what is the phasor? In a really simple word. What? Length? No. Length is just, it has phase as well. What's the phasor? It's a rotating bar. Good. Okay? Rotating carries phase information, bar carries length information. That's it. It doesn't have time. It's only amplitude and phase. Make sense? Angle. That's it. Doesn't have time information because it's called a steady state. It's always using the default frequency, and we're assuming all of them have the same default frequency. So we're not changing it. In order to simplify the calculation, we are trying to use the complex, which is the rectangle form, or the phasor form. Why is this simplifying things? Let me remind you about it really quick. This is another calculation you need to understand. Let me show you. A plus bj over c plus dj. Okay? In complex form. Ask you another question. Is this a sinusoidal wave? Yes. Cosine wave? Yes. This? Yes. Is this a sinusoidal wave? Yes. Sinusoidal wave? Yes. Okay? They're all sinusoidal waves. So for this thing, if I have a sinusoidal wave here, since you can convert it to this form, another sinusoidal form here, waveform over here, can you do the division operation easily for these two sinusoidal waves? Yes, because they are in the phasor form, and we only worry about the amplitude and phase. If you do this, who can tell me how to do it? It's very difficult. Okay? When you put the time in there, it's difficult to do the calculation. However, since we have the same frequency, we only worry about the phase and amplitude. So we don't want to do it in time domain. That's why I convert it to the phasor, to the rotating bar. So they are all rotating bars. It's easier to calculate. So now let's see how I do the division. There's another way. So remember last time? Let me just summarize everything over here for you to as a reference. So I just showed you here, right? How do we figure out that division, right? Since I multiplied 2 minus j on top and bottom, so I can convert the denominator to a constant. But there's another way to do that, okay? So let me just show you the method 1. A plus bj, that's method 1, c plus dj. C plus dj, method 1 I just introduced. C plus dj times what? C plus dj times what? C what dj? Minus dj. Top and bottom is not changing the value, but however you can convert the denominator to a constant. That's method 1. Okay? So in a rectangular form, you can do it without any problems. What about method 2? That's the beauty of phasors. A squared plus b squared that's the top. Are they equal? Can I just convert this to the phasor form like this? You just have to know how to do it for the exam 2, okay? It's the last problem. You just have to know how to do it. This to this. Same thing, same stuff. Amplitude, and angle. Make sense? What's next? Or method 3. I mean, it's not really a method, but it's just for you to look at, okay? Method 3. See? Angle instead of E here. They are exactly the same stuff. Exactly the same stuff. So why does this simplify things? You'll see this a lot in the homework or tutorials, but it may confuse you. Oh, it's doing a division. Why subtracting from the top? You know why? You know why? Can anyone tell me why? So let's just look at the phasor forms, okay? For these two, I mean for method 2 and
Is this subtraction with speed and EJ? Say,
yes.
So you can train like vector math?
Exactly.
Or like exponent math?
Yes. Can I extract these constants? You're not complaining about constants, right? Extract the constants in front of it, no problem. But for here, same frequency, steady state. That's why we can do EJ what? That's the whole point. That's the whole point of doing phasors. You can do multiplications and divisions easily. Make sense? So if you see this, oh, eventually I got a value like this: A angle 90 degrees on the top and 4 angle 40 degrees on the bottom. Can I get the answer immediately? Do you need to convert it to the rectangular form and then do all the calculations? So what's the result? Just let me know. Or saying, hey, the constants doing the division, the angles are doing subtraction. Why? Here's why, right? Questions on this? Anyone can tell me this equals what in the E form? So simple. Make sine wave multiplication division so simple. That's the whole point. We use phasors. Why all those talented engineers invented this, right, in the past. It's not trying to bore you, not trying to give you a lot of pains, not trying to torture you, right? It's beautiful. It's good. Let's move on to another problem. Since you guys are coming to class, so here's a benefit. You must know this. You must know this as well, okay? All these ones, it's a must. How many? 4. The fours, right? I totally have 4. Work through it. Just have to know how to do it. But there's one more thing that I want to talk about really quick before we move to another calculation. Okay. Here's a sine wave. This is still just the first problem, but I think there's one I missed. I didn't cover last time. Vt equals what? 110 cosine. Okay, if I ask you to convert degrees to radians, can you do that? Remember last time I talked about radians? What is radians? The parameter of the circle is 2 pi what? R, 2 pi r. So for the length, in terms of the length wise, this is the radian, right? This is the radian. So for the parameter of the circle, it has 2 pi of r's. So which means the length of the circle has 2 pi of like this much of length. Make sense? So for the whole circle, if this is the length here, you have like 2 times pi, which is like 6 point something of radians. Right? So it's using radians per second to evaluate or to count your angular velocity over here. But can you convert degrees to radians? How many radians here? How many radians? Angle-wise. How many radians? How many radians? You are getting extremely confused right now. A circle, the parameter of the circle is 2 pi r. You guys just got scared. This is middle school stuff. 2 pi r is the perimeter of the circle, right? Perimeter of the circle, right? Really? 2 pi r is the perimeter of the circle, right? So how many r's for the whole circle's lengthwise? How many r's? 2 pi's. What is pi? 3.14. So how many r's? How many r's lengthwise for the circle? 6 point something, right? Is this the r? Is the length of the r? Same length. How many radians? 1. It's just 1 radian. It's just 1 radian. So this angle is just 1 radian. It's just curved. It's not a straight line, but it's still still has a length, right? So that length is a radian. For example, if a bigger circle has a bigger radian. But the thing is, it's always representing the angle. So the 1 radian. Let me just ask you, 1 radian is how much angle here? 1 radian. What's the angle for 1 radian? Do I really know that? Let's just convert just use a regular problem. So degree converted to radian. So you know that a radian represents the certain angle, right? Because you have 2 pi radians for the whole circle to finish that 360 degrees. So 1 radian has 1 over 6.2 something times about 60 something degrees, right? 59 something degrees per radian. So this thing is 50 something, 58 or something. This is 360 divided by what? 2 times pi, right? That's 1 radian. 57 point something degrees, right? I don't know. Make sense? So 1 radian is this much degrees. If I tell you, hey, 60 degrees, how much radians? You know that. You can convert it. So 60 degrees, how many radians do you have for the, how many degrees do you have for the full circle? Yeah, you guys are scared. How much radians do you have for the whole circle? 2 pi. I told you, 2 pi r, 2 pi radians. So what's the radian here for that angle? How many radians for 60 degrees? I just assume an x, or you can calculate x, right? You can convert back and forth. If you have a radian, for example, the radian is pi over 3. You have heard about this a lot. Pi over 3 is what? 60 degrees, right? If this over 2 pi, is this equal to 60 degrees over 360? Are they the same? Yes, right? Yeah, 1 over 6. 1 over 6 on both sides. Make sense? Okay. So if it tells you the sinusoidal function, this is cosine, not sinusoidal. Okay, it's a sinusoidal function being shifted by 125 over 18 milliseconds to the right. How to deal with it? Shift to the right. Shift to the right, minus or plus. Just covered it at the very beginning of the class. So let me test you really quick. Shift to the right. You still have this kind of image in your mind. Shifting to the right, you're having something here. Delay or lead. Lagging or leading. Lagging, it's lagging, it's lagging. Okay? Plus or minus, see that? Shifting to the right. Plus or minus? Minus, yeah, minus, right? Minus. So this becomes what? Shifting to the right by this much time, and you are doing an angle shift or time shift? Angle shift or time shift? Time shift. So you want to shift for this whole thing or shift for t? Is that a delta theta or delta t? Delta t. So where do you want to put this shift? Vt equals cosine So after today's lecture, you got deeply worrying about your exam 2 right now, right? Tell me, where do you want to shift it? Keep in mind, never use something pi directly interact with the angles. It shows the angle, but just showing you a concept. But eventually, this is what? You can't just use degrees with like something pi's, right? They're not in the same domain. You just have to convert it. Convert it to the radians domain or radians unit. So they show you a degree. That's why it's confusing, right? They show you this, minus 60 degrees, but you cannot directly use it for the calculation. You know what I mean? It's just showing you this is a 60-degree phase shift. But however, you need to know there's no way that I can plug in that 60 degree into the calculation. You just have to convert it to something pi's because this is the radians. This is something pi times t. So this is the radians angular velocity. So eventually it's something pi. It's not something degrees. So you do this conversion. Eventually, if it's not exactly what you see as one of the options, you just have to convert it. So you have to know how to convert it back and forth, right? I'm pretty sure people will still ask questions about it later. But you get one answer. I'll just tell you. So for example, eventually I'm getting 110 cosine 120 pi t minus 7 over 6 pi, okay? Both in radians, perfect. I was looking at the options or choices. Dr. Lee, none of them are correct. What you can do? So look at it. Where is this angle? Always draw the coordinate here. This is a little bit over than 1 pi, right? So 1 plus 1 over 6 pi. So it's over. Oh, it's a minus. So it's actually over here. So what is this? Right? 30 degrees. Why? Because it's a minus angle. So it's rotating that way. It's minus. Remember the figure I just drew at the very beginning of the class? One more time. Leading or lagging? Leading or lagging? Lagging. Minus or plus? Minus. Minus or plus? Minus. Leading or lagging? Lagging, right? Lagging, pull it back. Lags 1 pi plus 1 over 6 pi. Okay? So cosine of this thing is cosine of this guy, positive or negative? Negative. See, this bar here is negative. It's negative domain. It's negative. So the cosine of this guy equals to what? Cosine of what? Same stuff. This is one of the choices. This is not. All right? So I think I covered pretty much everything, but the calculations for the other the rest of 4 problems, as these ones, will be the same. Since it's you use MASH, use node method, just use the same operations as how you did it with the linear circuits, resistors, same concept. So the only thing you need to know is all these operations for these complex numbers. I already showed you for one of the problems. We'll do more on Friday. But hopefully you can get things done by the due date today, okay, for homework 9.